Dear friends, Maths Aspirants Groups is a community of maths lovers, including UG and PG students, research scholars, as well as some teacher members also from various parts of India. We used to arrange several online problem solving sessions and online test series to help the students who prepare for different competitive examinations like JAM, NET, GATE, etc. Last year, we had conducted several such sessions. This year also, we are arranging such sessions. As all of you know, now it is again the time for of different competitive examinations. Notifications of NET examination and JAM examinations were out. We will begin our online problem solving sessions series of this year with today's class, and we have Ms. Nandana K. Vasudevan is with us for today's for handling today's session. Ms. Nandana did her BSc from Mercy College, Palakkad, and MSc from Cochin University of Science and Technology. She qualified UGC NET with JRF with All India rank 122. Also, she qualified GATE examination. She is currently a research scholar at Amrita Vidyapeetham, Coimbatore. I would like to express my gratitude and thanks to Nandana for being with us. She will discuss on the topic sequences of real numbers with you. As you know, sequences of real numbers and infinite series are one of the main topic from the real analysis portion for any competitive examinations. I will hope that today's session will be really a fruitful session for you. Once again, I welcome everyone to this program, and also I welcome for all the members of Maths Aspirants Groups, Ms. Nandana, to handle the session. Welcome, Nandana.
Thank you, sir. So no much official introduction required. So I'll start sharing my screen now. So I'll start my session officially. So my topic for today, I'll be handling both sequences and series. So today we'll be looking at sequences only, because as you know, if you have already learned these topics from your college, then you'll be probably knowing that it's not possible to stuff both the topics together. So we'll be looking at sequences only today. So we'll be just going through the important definitions, important results, theorems, whatever is required. And then we'll be looking at few problems that has appeared in old MSc exams or NET exam and all. Fine. So please do feel free to interrupt if you have any doubt with my explanation, or if there is any network issue or something like that.
Okay.
Okay. So we start with the definition of sequences. The most simplest way to define a sequence of real number is as a function. That is, it is a function which is defined from set of natural numbers to the set of real numbers. That is, its range is either natural numbers itself or some subset of real numbers. So we have few examples. We have plenty of sequences that we can form using real numbers. So some of the examples that I have picked out is set n, that is sequence 1, 2, etc. Then constant sequence, that is, instead of taking different numbers, I am taking all the terms to be a single value itself. That is constant sequence. Then Fibonacci sequence, which is something very common to us. Then we are going to discuss about limit of sequence. So when we are discussing the topic of sequence, we are more focused on convergence or divergence or whatever. That is what is more important when it comes to a sequence. So throughout, we'll be discussing about the ways to check whether the given sequence in which we are, the question which is given to us, the sequence which is there in that question, we'll be having the chance to check whether it is convergent or not. So here we define the definition of convergence. That is, if we are given a sequence xn and r, then it is said to converge to some value x to some real number x, if for every epsilon greater than 0, we can find some natural number n0 such that if I am taking the sequence terms after that n0, then for all those terms, the difference between that limit and the sequence value will be less than epsilon. In that case, we call x to be the limit of xn, and that xn is convergent. And in that case, we can also write it as limit n tends to infinity. For convergent sequences are constant sequence 1 by n. So since every term is a single value, obviously it will come that value itself. And 1 by n, it will be 1 by 2, 1 by 3. It is decreasing gradually and it will be tending to 0, almost like a continuous function itself. So as I told earlier, we are more focused on the convergence of a given sequence. So we are finding out ways through theorems or results, whatever required to check the convergence of a sequence. Squeeze theorem or San yn and zn sequences of real numbers such that xn less than or equal to yn less than or equal to zn, and that limit of the sequences which squeeze the sequence yn, their limits are known to be equal. Then the limit of yn is L. That is, the sequence yn is also convergent. And next we have what is called the Cesaro's theorem. According to Cesaro's theorem, if xn and yn are sequences of real numbers with xn converging to x and yn converging to y, then limit n tends to infinity, x1 yn plus x2 yn minus 1 plus etc. plus xn y1 by n equals xy. So xy is already given to be limit of xn and yn. Then we have two theorems stated by Cauchi, Cauchi's first theorem of limits and Cauchi's second theorem of limits. The first theorem of limits, it is something relating to the arithmetic mean of first n terms of a sequence of real numbers whose limit is already known. It's if the limit of this given sequence xn is L, then the limit of arithmetic mean of first n terms is given to be L itself. And if we are closely looking into this first theorem of Cauchi's first theorem of limits, we can see that it is a special case of Cesaro's theorem. So here, as we can see, here we had two sequences. So if I take one of the sequences to be the constant sequence with constant term 1, then it will obviously give this Cauchi's first theorem result. Then next one is Cauchi's second theorem of limit. When we were talking about first theorem, we said it was limit of arithmetic mean. And when it comes to Cauchi's second theorem, it is the limit of geometric mean of first n terms. So if xn, so especially when we are talking about geometric mean, it is the nth root. So in order to take nth root, it is required that the terms which appear inside the root should be strictly positive or non-negative. So here we are taking only the case of positive real numbers. So let xn be a sequence of positive real numbers. If limit n tends to infinity xn equals L, then limit n tends to infinity geometric mean of first n terms equals the same limit as that of xn itself. Next, we move on to what is called subsequence. So if in order to define a subsequence, so we say subsequence of a sequence. So which means that to define a subsequence, we should already have a sequence which is given. So if xn is a sequence of real numbers and n1, n2, etc., nk are natural numbers such that they are in increasing order, then the sequence, that is, I am taking those sequences with index n1, n2, etc., nk. Those values are only taken from that given sequence. So such a sequence is called subsequence of xn. To be more simple, I can say that it is an infinite subset of the given sequence. So again, we are going to discuss about convergence. So if there is something like subsequence, is there a possibility to check the convergence of that given sequence? That is what we are going to look. So that is what this theorem states. So if xn is a sequence and xnk is a subsequence of that given sequence, then we have the result that xn converges to x implies its subsequence converges to x. That is, the sequence and the subsequence converges to the same limit if they are convergent. But on the other hand, the converse, that is, I have a sequence and I have a subsequence. If that subsequence converges, then is it possible to say that the sequence itself converges or not? So that is what is given below. That is, converse of the theorem is not true. We can show this using a very simple example. That is, I take my sequence to be minus 1 power n. And I am choosing my subsequence in such a way that I am taking only the e. So we were discussing about the case when a sequence converges and how it relates to the convergence of a subsequence. So there arises a question, that is, we have already told that the converse is not true. That is, simply by taking a particular subsequence which converges, we cannot say that the sequence as such converges. So there arises a question, then when will it converge? When will that given sequence converge? So in order to show that, we'll have to take a stronger condition. That is, we'll have to check if every subsequence of that sequence converges to x. But practically that is not possible. As you can see, a sequence has infinite number of terms. You can form infinite number of subsequence from that. You can avoid few terms, just one term you can avoid. You can avoid 2 terms and take a subsequence. You can avoid 3 terms and take a subsequence. So there are infinitely many possibilities for taking subsequent. So it is not practically possible to check each and every subsequence converges to x or not. So we are going to somewhat better condition. So here we'll be defining something called the tail of a sequence. That is, if I have a sequence xn and m is some given natural number, then the m tail of the sequence is the subsequence defined by xm plus n. That is, I am taking the sequence or the subsequence which comes, that is, I am taking the terms that comes after xm, all the terms that comes after xm. So as per the definition, it is also a subsequence, but the only point is that I am taking all the terms continuously after that particular value xm. So here, when we are defining the theorem, it is little more easier to check convergence. That is, xn is a sequence and m is some natural number. Then the sequence converges if and only if m tail converges. So for any natural number m, if you are able to show that m tail converges, then it is a necessary and sufficient condition to show that the given sequence also converges. Then we come to certain types of sequences which will help us in checking this convergence easier. So among this, the most important one, first one is bounded sequences. So just like we state for functions, when we talk about sequences, it also has bounded above, bounded below, and simply bounded condition. So a sequence is said to be bounded below if there exists a natural number m such that xn is always greater than or equal to m for all n, and similarly bounded above if there exists capital M such that xn is less than or equal to that m for all n. And the sequence is said to be bounded if it is both bounded above and below. And as we can see, always a convergent sequence is bounded. But the converse is not true. We can again take the example that we have taken previously, that is minus 1 power n. The sequence is oscillating between minus 1 and 1. So its upper bound, we can take it to be 1, and lower bound, we can take it to be minus 1. It is bounded, but it is not convergent. That is, it clearly shows that every bounded sequence need not be convergent. So again, there arises the next question. Then when will a bounded sequence be convergent? So we'll be talking about that in the next step. So in order to explain that, we need one more condition. So to explain that, we'll come to one more definition, which is called as monotone sequences. That is also something that we have used along with functions, monotone functions. So if we have a sequence xn, it is monotonically increasing or simply increasing if x1 less than or equal to x2 less than or equal to etc. less than or equal to xn, etc. And it is decreasing if x1 greater than or equal to x2, just like we are writing it in decreasing order, or increasing if it is already in increasing order. And it is said to be monotone if it is either increasing or decreasing. Then we have three famous theorems, and in the first theorem lies the answer to our previous question, that is, when will a bounded sequence be convergent? So that is where we have monotone convergence theorem. That is, a monotone sequence of real numbers is convergent if and only if it is bounded. That is, a bounded sequence should also be monotone to show that it is convergent. So that is the answer to that question. Then we have what is called monotone subsequence theorem. That is, every sequence, as we can see, every sequence need not be monotone. It may or may not be monotone, but it always has a monotone subsequence. We can always find a monotone subsequence in every sequence. Then we have Bolson theorem, which states that every bounded sequence has a convergent subsequence. That can be, the proof of this is simply taken from these two theorems. Just adjoining those two statements, you can obtain the Bolson theorem. Then we define what is called Cauchi sequence. So a sequence xn, it is said to be Cauchy if for every epsilon greater than 0, we can find a natural number k such that for all m and n that exceeds that k, xm and xn, the difference between those two terms is always less than epsilon. And why is this Cauchy definition of Cauchy sequence important? That is given by Cauchy criterion. That is, a sequence of real numbers is convergent if and only if it is Cauchy. That is, if we are asked to check whether a sequence is Cauchy, it simply means that the question is whether the sequence is convergent or not. That's all. Then we have inductive sequence or recursive sequence. So this is something that should be handled with care, because these sequences are not, the convergence of these sequences are not that easily calculatable. So we'll just check the definition of recursive sequence first. That is, a sequence whose first k terms are already given. Their values will be previously defined, and the next term onwards will require the previous k terms which are given. That is, when we were defining a sequence, we said that it is a function from set of natural numbers to set of real numbers. So whenever we say that it is a function, we can find a defined formula for that. That is, in order to find the nth term, I'll be having a formula for that. So if I am putting my n value, if n is 5, I'll get what my fifth term is. But when it comes to inductive sequence or recursive sequence, if suppose I am given the first two values, I cannot jump to 7th term or 8th term and find the value. I have to gradually calculate one by one values to obtain the larger values. So that is where inductive sequence or recursive sequence becomes different. So one of the most common recursive sequence that we know is Fibonacci sequence. So it is defined as 1 for n equal to 1 and 2. And from there on, from the third term onwards, what we are doing is we are adding the terms which are just prior to it, the two terms which was prior to it. So that is how we obtain Fibonacci sequence. And when we are solving the questions, we can see that there are many questions that comes from recursive or inductive sequences. But in almost all those cases, they have given the sequences for which the first term is defined, and the second term onwards, it is defined in terms of an alone. That is, an plus 1 is defined in terms of an alone. Here we are using fn in terms of fn minus 1 and fn minus 2. That is, we need two terms. But when it comes to exam point, they have given only sequences for which only one term prior to it is used. So we'll be looking at such questions. Then we check the definitions of limit inferior and limit superior. So if we have a sequence xn, the most general definition to it, that is a limit inferior of xn, which is represented either by limit lower bar or limit inf xn. So it is the supremum of, that is first we are taking the infimum of each of the sequences. That is first we are taking set A1, A2, etc. We are finding the infimum. Keep it aside. Then we are taking the set A2, A3, etc. That is we have avoided the first term. We are taking A2, A3, etc. We are taking the infimum. Keep it aside. Again, so we are avoiding one by one terms from front and we are taking the tail sequences. So we are finding the infimum of tail sequences. We are taking it as a whole set and we are finding the supremum of that set. That is how we calculate limit inferior. And similarly for limit superior, we are finding the supremum term for each m tails, and then among those supremums, I am finding the infimum. That is how we calculate limit superior. There is one more easier way to compute limit inferior and superior, which will come in the next slide. So for a bounded sequence in particular, if you are making it more formal, then we can say that the limit inferior of xn, it is the supremum of the set V, which is the collection of elements such that xn less than V for at most finite number of m. That is, the number of xm's that are less than that V is at most finite number. So such, when we are taking the collections of such V, among those collection of V, I am taking the supremum. That is my limit inferior. Similarly, when it comes to limit superior, I am taking the collections of W such that when W less than xm, it is always for at most finite number of m. So taking such collections of W, I am taking the infimum of that set. That is what my limit superior is. So don't get upset with all these heavy definitions. We'll see a simple way for that. So if we are given a sequence xn, we are finding the limit points. That is one important thing that you should note down. It is not limit, it is a limit points. So that is where we require the definition of limit point. Can someone tell me what the definition of limit point is?
A point is said to be a limit point. We are able to find a neighborhood for that point. In the neighborhood, we are able to find another point other than that particular point.
Yes, that is it. So we are finding such kind of limit points. So among all those limit points, I am taking the least value. That is my limit infimum. And similarly, among all those limit points, I am taking the maximum. That is my limit supremum. So when it comes to questions and all, I think this will be a better option, because taking each and every m tails and checking the infimum and then taking the supremum, that will be a very tedious process. So I think this will be a better option. And here we have a result, that is infimum xn is less than or equal to limit infimum xn less than or equal to limit supremum xn less than or equal to supremum xn. So now, so far we have discussed, that is, we were discussing about limit supremum and infimum. So based on that, we'll just classify the sequences that are available around us. Okay. So limit supremum and limit infimum, they can be equal or unequal. So if they are equal, they form the limit of that sequence. That is, the sequence is having one single limit itself. So that can occur as three different cases. That is, the limit is a finite value, it is minus infinity, or it is infinity. These are the three possible cases. So when it is a finite value, we can say that the sequence is convergent, which means it is monotone and bounded. And when it is minus infinity, so I have attached one example with it for easy understanding, that is 1 by n. So here we have only both limit supremum and infimum as 0 itself, so which is convergent to 0. Then next case is limit is minus infinity, then the sequence is diverging to minus infinity, which is monotonically decreasing, and at the same time it is unbounded below. That is why it has gone to minus infinity, because it is monotonic, and if it is bounded means it will obviously be convergent, as we have told. So here it is monotonically decreasing, and at the same time it is unbounded below. For example, that sequence minus n. And third type is limit is infinity. There the sequence is divergent to infinity, like in case of sequence n. So the sequence will be monotonically increasing and at the same time unbounded above. So these were the three cases when limit supremum and infimum are equal. Now, if they are not equal, then we have four possible cases. That is, limit supremum and infimum both are finite values. Then either one or both are infinity. So the first case, when limit supremum and limit infimum are finite values, then it is called a finitely oscillating sequence. Like we have taken minus 1 power n. So its supremum is 1, limit supremum is 1, and limit infimum is minus 1. And next three cases, we collectively call it oscillating infinitely series. That is, the first example which we have is the case when limit infimum is constant and limit supremum, it goes to infinity. So let's see the example. 1, 1, 2, 1 by 2, rest is 3, 1 by 3, so on. So when I'm taking the odd case, odd terms alone or odd term subsequence, we can see that it is 1, 2, 3, etc. So it is going to infinity. And when I'm taking the even terms, it is 1, 1 by 2, 1 by 3, 1 by 4, etc. So it will be coming to 0. That is, limit infimum is finite and limit supremum is infinite. Similarly, the third example is like minus 1, 1, minus 2, 1 by 2, minus 3, 1 by 3, etc. So there, just the opposite case, that is limit infimum is going to minus infinity and limit supremum is 0. And the fourth case, that limit infimum and supremum both are going infinitely, just like minus 1 power n, n. So when I'm taking the odd terms, it will be going like 1, 3, minus 1, minus 3, minus 5, minus 7, etc. And when it comes to even terms, it will be 2, 4, 6, 8, etc. So from both sides, it is going to infinity. So these are all about limit supremum and infimum. So that's all about theory part. Is there something that I should re-explain or clarify? If not, we can proceed to the problems part.
Ma'am, I have a doubt.
Yeah, ask.
In the slide of monotone convergence theorem, you said that, can you please open the slide?
Yeah, 1 sec. This
Yes,
fine?
ma'am. Yes, ma'am.
Mm.
So, what is the definition of monotone sequence? I mean, is it like the tail of the sequence must be increasing or decreasing, or the whole sequence must be increasing or decreasing?
The whole sequence is increasing or decreasing.
Then the theorem said that a monotone sequence of real numbers is convergent if and only if it is bounded.
Yes.
But oh, sorry, ma'am. Sorry, ma'am.
Is there a confusion?
No, it is right. Correct.
Okay. Any other doubts?
Teacher,
No.
could you please explain limit inferior and limit superior?
Sorry, you're not audible.
Would you please explain limit inferior and limit superior?
You want me to repeat that?
Yes.
Okay. I'm facing a slight issue with my laptop, so kindly forgive me for the delay that it's showing. Okay. So are you confused with the whole definition, or you want me to explain with an example or something like that?
We can
Nandana,
Sir?
yeah, Nandana, we can share the notes of that so that they can go for the definition later.
Yeah, sure,
We
sir.
can-
Okay, so I'll make it clear to you with a very simple example. Let us take the sequence -1, 0, 1, -1, 0, 1. It keeps on repeating. Okay, so if I'm taking that, as per the definition, we can see that -1, 0, 1. All these three are limit points of that sequence. Am I correct or not?
Yes.
Okay, so all these -1, 0, and 1 are its limit points. So among that, the least value, which is the least value, -1. So that will act as the limit infimum. And among that, the largest value, which is 1, will be the limit supremum. So when it comes to the convergent case, both these limit infimum and limit supremum are equal. Only when it is not convergent, we'll be having a confusion with this limit supremum and infimum. Okay.
Yes, ma'am. Clear.
Okay. So I think we can go to problem session, or we'll run out of time. Okay. Okay. So we are beginning with the problems. I'll show the questions first. Which year or for which exam the problem has come. It is also shared. So you can tell me the answer which you feel like it is the answer, and do feel free to share the idea that you have used to obtain that answer, and then we'll go to the final explanation of that question, right? So this is the first question. The sequence cos of half tan inverse minus n/2 whole power n is. So the question is regarding monotonicity and convergence of that sequence. So those who have ideas regarding the answer, you may please unmute yourself and say. Don't be bothered whether it will be right or wrong. You can just say, this is just a discussion session, so you may please share your answer even if it is wrong.
Dear participants, you can use chat
Can
box also to
can
comment
I
the answer.
decide it is neither convergent nor divergent, nor monotone?
You mean fourth option? The person who answered. Okay, any other answers?
Ma'am, monotone but not convergent.
Monotone but not convergent. Okay, so we have got option 4 as one answer and option 2 as an answer. Okay, any other answers?
Not convergent, but monotone is not. I don't know whatever it is monotone.
Monotone, but you're not sure about convergence, right?
Yes.
Okay, so option 1 or 2. Okay, fine. Any other answers?
Ma'am, I too think that the third option, convergent but not monotone.
Convergent but not monotone, third option. Okay. So I think we have got all 4 options. I think it will be better we go to the answers rather than confusing it even more. So This
Ma'am, option 3.
option 3, convergent but not monotone. Okay. So can I move to the answer?
Yes, ma'am.
Okay. Answer is option 1. So we have not used any of the methods that we have discussed so far. So actually, I have chosen some problems that have used some different techniques apart from these theorems. Direct application of theorem, I think you can do it by yourself. So I've chosen something which are different from these. Don't feel that I have discussed questions which are not at all related to the theory that I've taken. So this is a different kind of question. So if you remember the graph of inverse tan or arc tan, you can see that it is a function that is monotonically increasing, which is asymptotically going to minus pi by 2 and plus pi by 2. So that is how the graph shape looks like. And also tan inverse, it has the same sign as that of x. So that is one idea that we'll be using. Then the second idea is that cos of minus x is cos x. That is, cos does not change sign. So now, the sequence that we had was cos of 1 by 2 tan inverse minus n by 2 whole power n. So here, as minus n by 2 whole power n, that is also according to, it is changing sign according to the power. So accordingly, here tan sign will also be changing as plus or minus. But since that does not affect cos, we are going to take it as 1 by 2 tan inverse n by 2 power n itself. Okay, that is the first turning point that comes to this question. Then we are building the function step by step. Okay, that is n by 2 power n. It is increasing from, so I am putting n equal to 1. It will be 1 by 2. And as we can see, it is increasing to infinity. It is going unboundedly. Then taking tan inverse, it is actually, it's not required to calculate the exact value. The approximate value will be enough, but in order to get more clarity, I've taken the exact value. So it is increasing from 0.4636 to pi by 2, which is around 1.5703. So here, this value is near to 0, and here it is near to pi by 2. So when taking cos, it will be a decreasing graph along this area. So it is decreasing from 0.9732 to 0.7074, which means it is monotonic, and at the same time it is convergent. This may seem little problematic because you are seeing these values. It may not be possible to calculate the values at that time, but that's okay. I have taken this just because it is not using any of these theorems or results that we have discussed. So we'll go to the next question. So xn is a sequence of real numbers such that limit n tends to infinity, xn plus 1 minus xn is a constant term. Then what can you say about sequence xn by n? So answers that you feel like saying.
Ma'am,
Yes.
can you please show previous question?
Previous
Option
question.
C, converges to C.
Converges to C. Okay. The person who asked for previous question, is it enough we are discussing it again in the end, since we have already started with this question?
I have only one doubt, ma'am.
Yeah, tell me.
There you have prescribed your region to pi by 2, right?
Yes.
Only pi by 2 to pi by 2. But you didn't give any interval in the question now.
I didn't get your doubt.
Ma'am, tan curve is continuous only in the region minus pi by 2 to plus pi by 2. Open interval.
It's not tan, it is tan inverse.
Okay, ma'am. Okay.
Is that okay?
Okay, thank you.
Ma'am,
Yeah, tell me.
in given question, tan inverse minus n by 2 is there.
Which question are you saying? This
Previous.
question or previous question?
Previous, ma'am. Previous question.
Okay. Yeah, tell me.
Yeah, ma'am. There is a minus n by 2 raised to n in given question.
Yeah, that's what I was saying. That is when we are taking negative, that is even when we are taking odd n, we can see that that negative is still remaining there, isn't it? So what happens, since tan inverse is having the same sign as that of x, that tan inverse minus n by 2 power n, for odd values, it will be negative. But since it does not affect cos, we are taking it to be n by 2 power n itself.
Yes, ma'am.
Okay.
Got it.
I know it may not feel that convincing for you, but that is how this question proceeds.
Okay.
So can we go to this question? I got one answer option that converges to C. Someone said that. So any other answers are welcome.
Converges to D.
Option B, ma'am.
Converges to 0. Okay, I think I'm getting some answers in the chat
Option
box
2, ma'am.
also.
Option 2.
Bounded but
And
not convergent.
is bounded but not convergent.
Ma'am,
Okay,
B, ma'am.
so
Option B.
option B. So I think we are getting option B as plenty of answers. Okay. Anyone wants to explain the way you got your answer?
Ma'am, I took the sequences n plus 1. So the general term is for xn plus 1, the term will be n plus 2. So I got limit n tends to infinity, n plus 2 minus n plus 1 will be 1. So I took the sequences, general sequences n.
Yes. Okay, that is the same answer that I have got. So rather than going for theoretical answers, sometimes taking counterexamples are best.
But I don't know whether, I give the example for counter for all other options.
Yes.
So by that way, I neglect the 3 options, but don't know how to do that answer.
Yeah, but that is enough. When it comes to a single answer, that is if you are able to strike off 3 options, then it is enough to show that that one is enough. But if you have striked off only 1 or 2 options and then again 3 or 2 options are left, then maybe you will require theory also. So here it was from part B, that is it is a single answer, multiple choice question it was. So for such questions, this is enough. Okay, even I have gone for the same way. I haven't gone through that theoretical side much. So I've taken the counter example as xn equal to n, which means our xn by n will be 1. So according to this option, when we are checking it out, so this sequence, it turns out to be a constant sequence, which is 1, 1, 1 itself. So it is bounded and convergent, and it is converging to 1, not to 0. So using that, we can say that options 1, 2, and 4 are wrong. And from which we get that 3 is the final answer. Okay. Is that clear?
Ma'am, can you
Clear, ma'am.
repeat it
Clear.
once more?
Sorry, I couldn't hear you.
Ma'am, can you explain it?
Sorry, I'm hearing a female voice. Please say.
Ma'am, can you just explain it once more?
Yeah, sure. So what I'm doing is I'm taking my xn to be the sequence n itself. So here my xn plus 1. So I need to take a sequence that satisfies this condition. That is all what I need. So for my ease of convenience, I'm taking the most simplest sequence that I have, that is xn equal to n. So here it will be n plus 1 minus n, which is 1. So the sequence is always 1. Limit n tends to infinity, this sequence is also 1. So which means, according to this question, the sequence that I've taken, it has satisfied this condition. That is xn equal to n. Now I am checking for xn by n. So it is n by n, which is sequence 1, 1, 1. That is constant sequence 1. So it is bounded, it is convergent, and it is converging to 1, not to 0. So using that, we can say that first, second, and fourth options are wrong. Is that okay?
Yes, ma'am.
Okay. Okay, here is the third question. That is, xn is a convergent sequence of real numbers, not converging to 0. Which of the following is or are true? So answers, anyone has any answer? One or more answers?
Option 2.
Option 2, that is xn is non-zero for infinitely many n. Okay. Any other answers? 1 and 3. Someone has commented 1 and 3. Okay. Any other answer? Option 1. If there are no more answers, we can go to the discussion. Shamita is option 1. Okay. Option 2.
Ma'am, I go through option 1.
Sorry, I can't hear you.
Ma'am, option 1.
Option 1. Okay. So if the answers are over, I'll go to my...
Miss, 1 and 2, I think 1 and 2 are almostly same, but I can't compare this both.
Yeah, that's okay. We'll go to the detailed solution. That's fine. So I think I'll go to the answers. I'm getting mixed answers 2, 3, 1, 2, 4 and all. So we'll go to the answers. So for option 1 and 3, I've taken counter examples 1 minus 1 by n. So we'll check here. That is xn is non-zero for all n. So 1 minus 1 by n, it is a sequence which is converging to 1. So it is satisfying the condition that is given in the question, right? So 1 minus 1 by n, for n equal to 1, we get x1 equal to 0. So that violates our condition or the option 1. Similarly, when we are taking 1 minus 1 by n, it is a non-negative sequence, right? It is a non-negative increasing sequence that is going from 0 to 1. So its infimum is 0 itself. So it strikes off option 3 also. Now we'll be checking for 2 and 4. So as sequence xn converges, and we are told in the question that xn is converging but not to 0. So it is having a limit which is non-zero. Then we can find infinitely many non-zero terms that are tending to it. So which means there are infinitely many non-zero terms. So option 2 is right. And when it comes to option 4, we have this result, that is xn, sequence xn is convergent to x, implies sequence mod xn converges to mod x, but converse is not true. Very simple example that we can again take is minus 1 power n. So minus 1 power n modulus converges to 1, but the sequence is not converging to x. Okay, so using this idea, if xn is converging to x, we can say that limit mod xn is mod x, which means limit supremum and limit infimum mod xn is mod x itself, which is clearly greater than 0 as x is a non-zero value. Thus, we get that option 2 and 4 are right. Okay. So, any clarifications?
Ma'am, can you explain the second option?
Yeah, that is, if xn is converging to x, we can always find infinitely many terms close to that x value, isn't it? So here, as the point to which xn converges is non-zero, we can find infinitely many terms which are non-zero, which are close to its neighborhood. So that is the simple idea, just like we are taking the case of limit point and all. It is having sufficiently many terms which are almost close to it. So here, since the point to which it is converging is non-zero, we can find infinitely many non-zero terms. Is that okay?
Yes, okay, ma'am.
Okay. So next question, it is something that involves greatest integer function. So if xn is a sequence defined by, the term is given to be the greatest integer of 5 plus n by 2n, then what is the limit of xn? This is comparatively an easier question.
1 by 2.
1 by 2. Okay. Any other answers?
Yes, 1 by 2.
0.
0. Ma'am, 1 by 2.
1 by 2.
Ma'am, 1 by 2.
Okay.
Hello, ma'am.
Yes.
Ma'am, can you show me the previous two questions? Means last two previous question means the limit question. Limit n tends to infinity x n plus 1 minus xn. I can give a proof of this. My proof is valid or not. So I check.
For which one?
Sukanta,
Option?
Nandana, one
Yes,
minute.
Sir.
Sukanta, you can send me that proof. We can discuss it later because otherwise we will be short of time for the
Okay, sir.
remaining discussion.
Okay, sir.
Okay, I
Yeah, you can continue.
appreciate your way of finding new proof between this. Don't worry, we'll discuss it later. Okay.
Okay.
Oh, okay. Oh my God. Okay. So answers, we were talking about this question. So we have got mixed answers as 1 by 2 and 0. So anyone who has answer 1 or 4? Here, since the question is regarding limit of that sequence, we can have only one answer. That is for sure. So we have got option 2 and 3. Okay. Answers are coming in chat box also. Fine. Okay. So I think I'll go to the explanation part. I've done it in two ways. First one is by computing it itself. Because taking small values, it's fine. So I've taken x1, x2, etc. So it is greatest integer function. So first thing that you can see is that the terms in xn are all integers. So it is not possible to get the limit as half there. That is one point that you should see. So here when we are taking the values 1 by 1, 1, 2, 3, etc., we see that it is decreasing from 3. Then next 4 terms are 1. Then it becomes 0. Then throughout it comes 0 only. So the sequence goes as 3, 1, 1, etc., 0, 0, so on. That is one way, or you can do it by normal computation itself. That is xn, I take it to be 5 by 2n plus 1 by 2, which is by splitting these two terms. So when I'm taking the limit, this value, that is 5 by 2n, it tends to 0. So my term will be greatest integer of half, which is 0. So the answer is 0. Is that okay?
Yes, ma'am. Okay. Ma'am, can you use the inequality? Means the integer, this box function is less or equal to this value and greater than this value minus 1?
I didn't understand what you said.
I say, ma'am, box of x is less or equal to x and greater or equal to x minus 1.
Box of, I still didn't understand what you said.
Means the greatest integer function is less or equal to this value and greater than x minus 1.
No, when you're taking greatest integer function, it is not less than or equal to. The value of that function is that integer itself, right?
Yes, ma'am.
Okay.
So it
Ma'am,
satisfies
can we do like
this.
this? It is a monotonic decreasing sequence bounded below by 0.
Yes, yes, that's it. Okay. The person who was talking just before, is it okay now? I hope I can go to the next question. Next, it is a question to find the limit supremum and limit infimum. So we are given the sequence term, that is an is n power sine n pi by 2. So you have to find the limit supremum and limit infimum.
Fourth option, ma'am.
Fourth option, that is supremum is infinity and infimum is 0. Okay, that is one answer. Then
I got option 1, ma'am.
supremum as 1 and infimum as minus 1. Is it?
Option 4.
Option 4.
Okay.
Ma'am,
Any other
option
answers?
4. Option 4.
Okay. Any other answers other than option 4? One of you told it as an option 1. Any
Option
other
4.
answers? Okay. So that is going, more answers are converging to option 4. So I think we'll go for the answer. So we are given n power sine n pi by 2. So we can see that n values are natural numbers that we are taking, 1, 2, etc. For that n values, it is possible to find the sine value, right? So we'll keep this base n apart. We'll just check this power, that is sine n pi by 2. So we can see that for even powers, that is even n, the value becomes n pi, right? N pi or k pi, let's say k pi. So it will be 0. And similarly, if it is going for n equal to 1, 5, 9, etc., it becomes 1. And similarly, when it is for n equal to 3, 7, 11, etc., it becomes minus 1. So now, so these are the powers, possible powers that it can have. So we are going to the sequence term, that is n power sine n pi by 2. So again, when we are applying this, we get that for n values 1, 5, etc., the value is n power 1, which is n itself. Then next one, for n equals even numbers, it becomes n power 0, which is 1. And the third case, when n is 3, 7, 11, etc., it becomes n power minus 1. So it becomes 1 by n, right? So what happens? This sequence, that is the first set where 1, 5, n, etc. For that set, it is going to infinity. Limit is going to infinity. In the second case, it is a constant sequence, which is staying constantly at 1 itself. And in the third case, we see that the sequence is decreasing towards 0. So when we are taking these three subsequence, they have 3 different limits. So this is where our definition of taking minimum and maximum of limit points for finding limit supremum and infimum is important, right? So we have 3 different limit points here, that is my infinity, 1 and 0. So among this, the maximum value is infinity, so limit supremum is infinity, and minimum value is 0, so limit infimum is 0. So we get that answer is option 4. Is it clear?
Yes, ma'am, got the idea.
Okay.
Ma'am, can you explain case 3 only, ma'am?
Yeah, sure.
Ma'am, will you share your notes?
Yes, sure. I'll be sharing
It is
it to
difficult
Vinod,
to
sir.
it is difficult to write continuously.
Yeah, it's okay. If when I'm showing the question, if it's possible for you to compute the answer, do that. You don't have to write down the whole thing. I'll be sharing it to sir. He'll be sending it to you.
Okay, thank you.
Okay. So when I'm showing the question, just make the calculations to find out the answer. That's all what is required. I'll be sending the PPT to you. Okay. So someone asked for repetition of third case. So when you see the graph of sine, you can see that it is going from when it is 1, it is pi by 2, 2, it is pi, 3, it is 3 pi by 2. So that is how the graph is oscillating. So when it comes to 3, 7, 11, etc., the value of sine is minus, that is sine n pi by 2. For these n values, it is minus 1. So here n power minus 1, which is 1 by n. And this subsequence, so it will be converging to 0. That is how it comes. Is it clear now?
Ma'am, still confused, ma'am. How to write 1 by n, ma'am? In third case, n power sine of n pi by 2. In third case, how to write 1 by n?
Yes, that is what we are saying. That is sine n pi by 2 is minus 1 for that case. That is n power minus 1, which is 1 by n.
Okay, ma'am, okay.
Is it clear now?
Yes, ma'am, clear.
Okay. So this is the next question. Sequence root 2, root of 2 root 2, root of 2, root of 2 root 2, etc. You have to find the limit of the sequence.
Ma'am, option 2.
Option 2, that is value 2 itself. Okay.
2.
Any other answers?
Ma'am, 2.
Okay. So anyone wants to explain how you got that answer? If not, I'll go to my explanation. So here I have written my sequence in the form of a recursive sequence. That is Sn plus 1 equals root 2 Sn, where I have defined my first term to be 1. So here what we'll be getting it, S1 is 1. S2, actually this was a mistake. I think I should have written it as root 2. Okay, so here it is root 2. I'll make the correction and send it to you. Okay, so the first term is root 2. Second term will be root of 2 root 2. Then next one, that term comes inside root 2 into that term, like that. It goes on like that. It is a recursive sequence. So since we are given that the sequence is convergent, we are asked to find the point to which it converges. So I take my limit of the sequence to be L. So I get that L equals root 2L. So the possibilities for L are 0 and 2. But as you can see, the value is only keeping on increasing. It is not decreasing. And at the same time, it is not possible to get the value 0 here unless any of the terms that is coming in between becomes 0. But from the very beginning onwards, we are defining using only terms like 1 or root 2 and all. So it is not possible to get the value, limit value to be 0, which means the limit of the sequence is 2. So answer is option 2 itself. Can I move on to the next question? Any clarifications required? Okay. So next question is something similar to this, but the slight difference is that rather than taking product, we are taking the sum. So, and not 2, it is 7. So to which point does it converge?
Ma'am, option D.
Okay, option D. I
Ma'am,
think
option
after
four.
doing, okay, option 4. I think discussing the question before and doing this immediately will make it easier for you. So any other answers other than 4? Okay, if not, I am going to the answer. It's same as the previous question itself. I am defining it like a recursive sequence. So here also, here it's fine. S1 I have taken to be, here also S1, my initial term I have had a slight confusion. It is √7. So from there onwards, from the next term onwards, it is defined as root of 7 plus Sn. So since we know that the sequence is convergent, the question itself demands the limit of that sequence. So I take that limit to be L and I am computing it. I get it as the solutions for this quadratic equation, L square minus L minus 7, which are 1 plus or minus √29/2. But as you can see here, there is no possibility that we are taking only the positive roots. So the limit will also be a positive value itself. It is going increasingly. So it's not possible to get a negative limit value. Since 1 minus √29/2 is a negative value, we cannot take that case. So a limit of the sequence will be 1 plus √29/2, which is option 4. Is that okay? Both are lookalike questions. I hope no clarifications are required.
I have little confused that how that Sn plus 1 become L.
I'm taking the limit throughout this equation. That recursive formula that I've taken, I'm taking the limit throughout. So here, when I take limit Sn plus 1 or limit Sn, it doesn't make any difference. Isn't it? Both shows that I'm finding the limit of the same sequence. So it is L itself. Okay.
Yes, ma'am, it's clear.
Okay. Any other doubts?
Ma'am, can you please show that it is a bounded, limit exists, we know by options, but we have to limit exist. It is
Your voice
bounded
is
and
breaking.
my question is, can you please explain that why it is bounded?
Okay. I'll come to those points. I have one more question in recursive sequence. Then I'll come to that. Is that okay?
Okay, ma'am.
Okay. So this is the next question in recursive sequence itself. So we have plenty of questions in recursive case. Most of the time they are asking the limit of the sequence itself. Okay, so you have to simply compute the limit. So this is one such question. So they have not defined x1 as such. They have told that x1 is greater than pi plus √2. So using that, you have to find the limit of the sequence. Any answers?
Ma'am, A. 1.
5 plus 1. Okay. Any other answers?
I got option C, ma'am. Pi.
Pi. Okay. Any other answers?
Ma'am, option B.
Pi plus √2. Okay. Any other answers?
Option 1.
Option 1 and option 3. I have got 2 answers again. Okay. Any other answers?
Option 1.
Okay.
It is option 1 only, 5 plus 1.
Okay.
By calculation mistake, I put 0 as in the right hand side.
Yeah, that's fine.
So I got 5 plus 1 only.
So far, no one has said option 4. I have got rest of the 3 options. Okay, so I think answers are over. I've got all 3 options. We'll go to the solution part. So just like previous questions, I've taken the limit of my sequence to be L and I've started my computation. So I get L equals pi plus root of L minus pi, and from which upon making certain arrangements, squaring, so and so, I get it as L equal to pi or L equal to pi plus 1. So since I have both these options in my question, I have to be sure which one is the answer. If one was avoided from that, it was fine. But since we have both these options, we have to be clear about which one is the correct limit. So there we use the idea where x1 is greater than pi plus root 2. So x2, next when we are computing the next term, it becomes pi plus, I am putting this term here since it is a recursive, and I get it to be pi plus 2 power 1 by 4, etc. xn greater than pi plus 2 power 1 by 2 power n. So that is how the terms are going on, which means as n tends to infinity, this value, that is 2 power n, it goes to infinity, which means 1 by 2 power n goes to 0, and evidently 2 power 1 by 2 power n becomes 1. That is, as xn tends to infinity, xn value is greater than 5 plus 1. So here, since each terms are greater than 5 plus 1, it is not possible to get L as pi, from which we reach to the conclusion that L equals pi plus 1. Is that okay? Is there any clarifications required? That is the sequence x1, it is decreasing, but at the same time, each term is greater than pi plus 2 power 1 by 2 power n. So why we have taken the limit as pi plus 1, avoiding the case of L equal to pi. Is it clear?
Yes, ma'am. Clear.
Okay. I thought I got disconnected. Okay. Any other confusions?
No, clear.
Okay. So I got a question regarding the boundedness of recursive sequence. We cannot always say, so I have already told when I was saying about recursive sequence, it is a sequence that should be handled with immense care, because just like this here, if we are not given some kind of detailing like this, in most of the cases, we'll be getting, that is for sequences which use only one term prior to it, in most of those cases, we'll be getting one or at most two limit values. So according to the initial values given or according to the way in which the recursive sequence is defined, we'll be able to fix which among those two limits is the actual limit of that sequence, or why we are avoiding the other value. We'll be able to define that specifically. Just like before, the previous questions and all, which one? Here. So here the terms are going as positive terms. So it is not, and at the same time, it is going increasingly. So it is not possible to get a negative limit. So we will be able to justify like that why we are not taking one limit value. And finally, we end up in the other limit value. So when it comes to recursive sequence, most of the time, so far when I've seen the question papers, they have asked to find the limit of the sequence, most of the questions. So you'll have to do like this only, like taking the limit to be L and proceeding like this, taking all the possible cases of that limit value L, and then checking which value can be taken. But there are cases when they are asking about the convergence of that given sequence, but that is very rare. I haven't seen in MSc question papers that. In some PhD entrances, I have seen that some question papers. But when it comes to that case, we have to be even more careful. We have to check whether the sequence is monotone or not. If it is monotone, then it is bounded or not. Then we have to use the theorem that we have learned and take that the sequence is convergent. Otherwise, it's not like that. If it is going like that, it is monotonically increasing without any bound, then it will be going to infinity. It will not converge. So handling such recursive sequences is a hard thing. So when it comes to checking the monotonicity, at times you can take that as a function itself. Okay, here that is, I'll be taking it as f of x equal to root 7 plus x. That is how I'll be defining it. So doing some adjustments to the recursive function that we have taken, we'll be able to check the monotonicity. But finding the bound of the sequence is, we don't have a strict idea for that. Most of the time what we are doing is we are substituting the values one by one and checking to which value it is going. Suppose it is, if the function is something like square root like this, then it will be gradually going to some value, very slowly it will be converging. So in that way it is possible, but in divergent cases it is not possible because the value will be going, it will be enlarging so and so. So checking boundedness of a recursive sequence, we don't have any strict or clear-cut idea for that so far. I have checked that, but I haven't found any. But monotonicity can be checked. But since I'm repeating once again, since you people will be asked about the limit of the sequence only, it will be enough to just substitute that limit to be L and then computing it. Is that okay? So you don't have to be much bothered about its monotonicity or boundedness since you are directly asked about the limit, right? Okay. So this was a question asked for net exam. That is, xn is a sequence of non-negative real numbers. Then which of the following is true? You can start saying the answers if you have got any.
Ma'am, 2.
Supremum xn equal to 0 implies limit xn square equal to 0. Okay. Any other answers? Yeah, tell me.
Option 3. First option.
Ma'am, option 1. Option 1.
Option 1, okay. Any other answers?
Option 1 and 3.
1 and 3. Okay.
Ma'am, option 1.
Option 1. Okay. Any other answers? Many of them are answering it as option 3. Option 2, option 1 or 3, option 2. Okay, so if answers are coming in the chat box, So I think I'll go to the explanation part. Here, one important thing that you should take care is that we are given limit infimum or limit supremum of xn, isn't it? In all the options, the if case is limit infimum or limit supremum. We are checking the then case, right? If then, so in that we are given limit supremum or limit infimum. So the problem when you are taking a counter example or something like that, it will be best if you are taking a non-convergent sequence. Then only you will be getting limit infimum and limit supremum different. Then only it will be easier to wash off the wrong options. So I'll show my counter examples. For option 1, I think the option 1, it was limit infimum x. So we'll check 1 and 3 together. Okay, limit infimum xn is 0. Then what about limit xn square and boundedness of xn? So let's see the counter example. Xn, I have taken it to be 0 when n is odd and n when n is even. So as you can see, it is a non-negative sequence along with the condition that limit infimum is 0 and limit supremum is infinity, right? So what happens? First case, limit xn square. Here xn square will be 0 for n odd and n square for n even. So can we say that it is convergent?
No, ma'am.
Okay. So there we have a counterexample. In the third case also, limit infimum is 0. But is the sequence bounded?
No, ma'am.
Okay, it's bounded below, but it's not bounded above. In order to say that a sequence is bounded, it should be both bounded below and above. So here, since it's not bounded above, it will act as a counterexample for third option. Now we'll see fourth option, that is limit infimum x square is greater than 4, then limit supremum xn is greater than 4. So let's take, I'm taking my xn square to be the constant sequence n. So my xn can be 3 minus 3, 3 minus 3, something like that, or 3, 3, 3, minus 3, minus 3, minus 3, something like that. That is, my xn will be 3 or minus 3 for all n. That is how I am taking my sequence. So its limit supremum is 3, not greater than 4. So that will be a counterexample for option 4. And final answer is 2, and the theoretical explanation, we are given that xn is a non-negative sequence, right? So when non-negative sequence is given, limit supremum is 0, it will obviously imply that limit infimum is also 0. That is only because the sequence is non-negative. Otherwise, we couldn't take this condition, that is limit supremum xn equal to 0 implies limit infimum xn equal to 0. Okay, so we get that limit xn is 0. That means limit xn square is also 0. Is it clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am.
So I'll go to okay. So this is the next question. If xn is a convergent sequence in R and yn is a bounded sequence in R, then we can conclude that we are asked about xn plus yn. This can also be given using simple counterexamples.
Option 2.
Okay, option 2. Any other answers?
Option 2.
Okay. Any further answers?
Option 2.
Okay, so answers are circulating around option 2 itself. Okay, so since we have not got any other options, whether in chat box, do we have any other answers? Everyone has given us option 2 itself. So for that, yes, I have taken my xn to be 1, constant sequence 1. It is converging to 1. And sequence yn, bounded sequence, I have taken it as minus 1 power n. So xn plus yn will be 0, 2, 0, 2, etc. So since our options were xn plus yn is convergent, but this sequence is not converging. It is keeping on oscillating. So this will be a counter example for option 1. Then option 3 and 4 also we have taken the same examples. So option 3 was that it has no convergent subsequence. It is enough to take odd terms separately or even terms separately. We'll be getting a convergent subsequence. Similarly, fourth option was no bounded subsequence. Again, we are taking odd terms alone or even terms alone. That will be enough to show the counterexample. And for the second option, if you need a theoretical explanation along with that, then since xn is a convergent sequence, it is always bounded. And sum of two bounded sequences is a bounded sequence. That is a simple result that we have. So using that, we can say that xn plus yn is bounded. Is that okay?
Okay, ma'am.
Okay.
Yes, ma'am.
Okay. So I'll move on to the last and final question that I have. Let xn and yn be sequence of real numbers defined by 0 less than x1 less than y1. And the way in which I have defined xn plus 1 and yn plus 1, it is slightly different from the way we have taken sequences before. It is not a recursive sequence also, because when we are defining a recursive sequence, we should be using the terms prior to the same sequence itself. But here we are using both xn and yn, so we cannot call it recursive also. So xn plus 1, it is the root of xn yn, and yn plus 1 is the average of xn and yn. Then what can you say about the monotonicity, convergence, and limit if they are convergent? So this was question that asked repeatedly for JAM 2017 and 2022. So you may be looking high, then how it is looking like this, it is option wise answer. It is because for one exam, they asked regarding monotonicity and convergence. And for the other exam, they asked about convergence and limit. So since it was a repeated question, I clubbed both the questions and I've made it like this. So you have ideas regarding it, please do share.
Option B.
It's not actually option. I'm asking about the monotonicity, convergence and limit.
It is not a monotonic sequence because when we define yn plus 1 as xn plus yn by 2, the term is like x1 plus y1 by 2, x2 plus y2 by 2. It's the average of two numbers. So I get a odd term of the sequence is monotonic increasing and the even term of the sequence is monotonic decreasing.
One second. You have taken it as x1 plus x2 by 2. Is it? That is not how we have defined it.
x1 plus y1 by 2, ma'am.
Okay. But with that, how can you say that it is not monotonic? I don't find that explanation that clear.
Oh, I thought x1 plus x2 by 2 is fine.
Anyone has anything to say on any of these monotonicity, convergence or limit of these two sequences? Converges to same limit. One of you has given in chat box. Okay, so that is the first answer that we are getting regarding this. Any other answers?
xn is decreasing, yn is increasing, converging to same limit.
xn is increasing and
Yn
decreasing.
is increasing, yeah.
Okay, that is one answer. Then
converge it and converge the same limit.
both converges. Is that what you're saying?
Yes, yes.
Okay, they converge to the same limit.
Yeah.
Okay. Any other answers?
Ma'am, when yn sequence is convergent, then xn is convergent, and limit of one sequence yn is must be less than or equal to limit of the sequence xn.
Limit of yn is less than or equal to limit of xn. Is that what you said?
No, ma'am, greater than limit of yn should be greater than or equal to limit of xn, and the sequence yn is convergent, then the sequence xn is convergent.
So how will you check the convergence of yn then? That is a trouble there. That is, we have defined both sequences in terms of both the sequences itself. That is where the problem is. I think I'll go to the answers so that your confusions will be clear.
Then the xn is also convergent sequence.
Sorry, I didn't hear you properly.
If yn is convergent sequence, then the xn is also convergent sequence.
Okay. So may I go to the answer part? The answer requires some explanation because there are three parts for this. First, we'll be talking about the monotonicity. So we'll be checking the first two terms for both these sequences. So x1, I'm taking it as root of x1 square, that is x1, x1. Since we are already given the condition that 0 less than x1 less than y1, I am replacing this y1, x1 with y1, which produces root of x1, y1, which is same as x2. Right, that is how we have defined xn. And similarly for y2, when I am taking it, y2 is x1 plus y1 by 2. So again, I am using that same inequality which we are given in the question. Using that, I get y2 less than y1. So for the first two terms, we see that x1 is less than x2 and y1 is greater than y2. Okay, now for the rest of the terms, we are using the idea that geometric mean is less than or equal to arithmetic mean. So as you can see, we have only two terms. So this is the geometric mean and this is the arithmetic mean. So for that, using that, we get xn plus 1 less than or equal to yn plus 1 for all n greater than or equal to 1. So we start from that point, that is, I am multiplying both sides by xn plus 1, which results in xn plus 1 square less than or equal to xn plus 1 plus yn plus 1. This is same as xn plus 2 square, isn't it? If I take the root, it will be xn plus 2. So I'm replacing this by xn plus 2 whole square, which is same as xn plus 1 less than or equal to xn plus 2. So that we get xn is monotonically increasing, isn't it? Here for 1 and 2, x1 and x2, we have found it as increasing, and for rest of the terms also it is increasing. Now for yn, here we have multiplied both sides by xn plus 1. Here we are adding both sides by yn plus 1. So it becomes xn plus 1 plus yn plus 1 less than or equal to twice yn plus 1, which is same as twice yn plus 1 less than or equal to twice yn plus 2 less than or equal to twice yn plus 1, which gives yn plus 2 less than or equal to yn plus 1, which means that here for the first part we have shown it is decreasing, and for rest of the terms we have also officially proved it that it is decreasing, from which we get that yn is monotonically decreasing. So xn is monotonically increasing and yn is monotonically decreasing. Now for the convergence part, so we have seen that xn is monotonically increasing. So using that, I have placed my xn's like this: x1 less than or equal to x2 less than or equal to x3, etc. And y1 also I have placed it from the other end. Okay, it is keeping on decreasing. So it is coming from this side. And at the same time, we have the condition that this condition, that is xn plus 1 less than or equal to yn plus 1. So using that condition, it becomes that for each terms, it will be coming like this. So if you have already learned the concept of nested sequences, we can see that x and yn, it is forming a nested sequences of closed boundary intervals. So if you have learned nested sequences of intervals, you would have also learned nested interval property. That is, if we have such a sequence of nested sequence of closed bounded intervals, then we can always find a real number such that it exists in every such intervals. Okay, so which means I am taking this to be my nested sequences. I can find some zeta which belongs to all these x and yn. So here, as we can see, xn is increasing sequence. But since I have a zeta somewhere here in that nested sequences, I can say that it is an increasing sequence which is bounded by zeta, bounded above by zeta. Similarly, yn is decreasing with lower bound zeta. So from where I got that zeta, it is from nested interval property. Okay, so using that, I can say that xn and yn are convergent. Okay, so we have obtained that they are convergent. Now we have to find what that limit is or how that limits are related. Okay, so for that, since it is convergent, I take my limit to be x and limit of xn to be x and limit of yn to be y. So I am putting it in either of the conditions that we have taken. I get x equal to root xy, giving x equal to y, or putting it in the other condition also, I get it as y equal to x. So one important point that you have to note is that unless you know that the sequence is convergent, you should not use this idea that limit n tends to xn is x or taking it to be some value L. Unless you are clear that it is a convergent sequence, you should never be substituting such a value and proceeding. Okay, so here only because we have obtained that these sequences are convergent, we have taken it like this. Okay, even in the recursive case, only because in the question it is given that the sequence is convergent, we have taken that limit to be L. Otherwise, we have to show that it is convergent and then only we can take the limit to be L. Okay, so that is how we obtain that limit of both these sequences are equal. So that's all about this question. Any part that you need repetition or any clearing, something like that? Convergence part. Okay. So there is something called nested sequence of closed bounded intervals. So only if you understand what that idea is, this part will be easy for you. That is, nested sequence of bounded intervals, closed bounded intervals means I'll have an interval x1, y1. It is a closed interval. Then I'm taking the second interval. It will be inside that interval x1, y1. Then the next interval x3, y3 which I am taking, it will be inside x2, y2. So that means it is going inside like that. Okay. So this part, that is x1 greater than or equal to x2, etc. And similarly from here, that we have received from the monotonicity part. And this one we have, that is here we have xn's increasing and yn's decreasing. But we have to show that it is having a bound. So we have already obtained that it is monotonic. Now if we have a bound, then we can say that it is convergent, right? So in order to show that, we are using the idea of nested sequence. So for nested sequence, we have a theorem or nested interval property which states that if we are having such a collection or such a sequence of closed bounded intervals, then I can always find a real number zeta which belongs to every interval. That is, it will be lying somewhat in the most inner interval. So it will be belonging to every interval which is taken. So here I have obtained that bound to be zeta. That is, xn is increasing. So since that zeta is in every in, I can say that zeta acts as an upper bound for this monotonically increasing sequence. Similarly, for yn also, since zeta belongs to every in, it will act as a lower bound for these set of values. So we can say that both xn and yn being monotonic bounded sequence, they are convergent. Is that okay?
Yes.
Okay. So if you are not aware about that nested sequence, then you will be having slight issue in understanding that. I don't know whether that has been taken in your college or not.
Actually, it was not in our syllabus. But I think it is some kind of subsets.
Your voice is echoing. I can't clearly hear you. If it's clear, then we'll wind up the session, or else I can repeat any part if required. I've taken this question because it was repeated twice, asking the same properties regarding that both sequences. So I have taken so much time to explain this question. I know it was a bit lengthy, but since I found it important, so I took that much time for that question. So if it's clear, then we'll wind up.
It's clear, ma'am.
Thank you, Nandana. Let me thank Nandana for today's wonderful session. Especially, I appreciate her selection of problems. It's a wide variety of problems were discussed in today's session, and also the necessary theory were explained. So I'm sure that for any serious student, today's session will be really fruitful. Now it is a time for discussion and making your comments. So please do come forward to express your views and comments. Also, you can ask your doubts regarding the preparations for competitive examinations. Please keep on your video on, as well as please introduce yourself first.
Ma'am, I'm Nandana K. I'm studying in
Nandana,
government.
Dina, 1 minute. Nandana, please switch on your video. Yeah, it's okay now. Yes,
Sorry.
Dina, continue. Yes.
Ma'am,
Yeah.
I'm Nandana K. I'm studying in Government Victoria College, Palakkad. First of all, thank you, Ms. Nandana, for taking us such a wonderful class. I'm really thankful that for giving us an opportunity for understanding the concept more precisely. Thank you, ma'am. It was really helpful for me to revise the concept which I have studied in the 3rd semester. Ma'am, I had a little remark. I think it's because of the lack of time that you were taking the topics fastly. So I find it a little bit difficult to understand them.
Yeah, I'll share the PPT. Maybe when you go through it, it'll be easiest.
Okay, ma'am. I will try to learn from it. Then I would like to thank Vinod sir for motivating us day by day for becoming more and more stronger JAM aspirants. Thank you so much, sir, for conducting such a wonderful session. Thank you.
Thank you, Dina. Others?
Sir, I'm
Hello.
Sindhu. Hello, sir.
Yeah, Cinda, continue.
I'm Cinda. I'm from St. Joseph's College, Devagiri, Calicut. And I'm a third year BSc Maths student. And I have to tell that this class today was very precise and clear. And the problem solving session was very useful. Since I think as a third year students just starting our fifth semester, we have got many new ideas and concepts regarding how to approach a problem in sequence. So, in this very limited time, so I'm very thankful to Ms. Nandana and as well as Dr. Vinod sir for introducing Nandana ma'am to us. Thank you all.
Hello, ma'am.
Hi.
Could you hear me?
Good evening.
Okay. My name is Altapam. I am from Government College Kattapana of Idki district. First of all, I am thanking you because for a wonderful section and was very useful for me. The first of all thing, I was mostly ignorant about most of the topics. Most of the topics were unknown for me. Means some of the portions were unknown for me. It was clear from this section. And also, I was wondered on answering of my friends because they are answering too faster and calculating much faster than me. Means I am not faster, but they are calculating how fast.
Altaf, you have gone mute.
Hello.
Yes.
Hello.
Now
Okay.
you are audible.
I wondered about their speed in calculation. Okay. I am thanking you for this wonderful section. Thank you.
Okay, thank you, Altaf. No need to worry about the speed of others.
Good evening.
Sir, you have gone mute.
Hello.
Yeah.
Good evening, all. I'm.
It's going mute, sir.
Hello.
Yes.
Yeah.
Now you are audible.
Okay. Good evening, all. I'm Adra Sundash from Convergent College. Hello.
Yes, you are audible.
Okay, ma'am. Okay, ma'am. And for me, this class was very nice and it was very helpful to understand. Thank you, ma'am. Thank you for giving such a wonderful class for us. And let me.
You have gone mute.
Sorry, somebody is creating problems. I don't know. Adira, please unmute again.
Okay, sir. Sorry, sir. It's getting unmute. Sorry, sir. Sir, am I audible?
It's okay.
Yeah, you are audible.
Okay. I'm Adira Sandosh from Government Victoria College. Thank you, ma'am, for taking such a wonderful class. It was really nice and it was very helpful to understand. And let me thank to us, sir, for conducting such a wonderful class for us. Thank you all. Thank you, ma'am, and thank you, sir.
Yeah.
Thank you, Adira.
I'm Abarna Lal. I studied in HMS NNS College for Women in Neramangara.
Gone mute.
Yeah, I think it's just a service problem. It's getting muted.
Mute. Yes.
Okay, actually, I'm a graduate and I'm thinking of, I have now competitive exams coming up in Maths. So it was a wonderful session for me as I could get to know more about this sequence because I was a bit lacking in this, like in real analysis sequence portion was a bit lacking for me. Like I don't know properly, but ma'am, today's session helped me a lot. And thank you so much for taking class for us, for all of us. And I also like to thank Vinod sir for helping us out and giving us this wonderful opportunity to study from our homes. So thank you.
Thank you, Aparna.
Hello.
Yes.
Yeah, you are audible.
Hello.
Two of them has come.
Yes.
My name is.
Yeah, Rasha. Continue, Rasha.
My name is Rasha. I'm coming from T.M.Govt College. First of all, I'd like to express my deepest gratitude to Nandana ma'am because this is the first time I was looking into the concept of sequence. I'm a second year student, and the concept felt really interesting. Even though I couldn't solve all the problems by myself, I could get an, it was a good exposure to the kind of questions that I should be practicing once I get a deeper understanding of the concept after watching the recorded video. I think I'll have to watch it again and again to actually grasp the entire sense of the concept. But I'd like to deeply thank also Dr. Vinod sir for giving us such a wonderful opportunity. Thank you. Thank you so much.
Thank you, Risha. The point that made by Risha is very good for a student. You have to keep on learning the things again and again to understand the things more better. Okay, others?
Hello. Am I audible?
Yeah, you're audible. Yes, yes.
Hello, ma'am. I'm Gopika from Zamorians Gurupam College, Kozhikode, and it was such a wonderful class today, and we all are really thankful to you to spend the valuable time of you, and it was very useful for us to prepare the jam. So we all are really thanking you.
Yeah.
Thank you, Gopika. Others?
Hello, ma'am.
Is Shikha?
Hi. Your camera is off.
Now am I not visible?
Yeah, you're
Yeah, your audio is audible, but your video is not visible.
Shikha, if possible, please keep it. Yeah, it's okay now.
Yeah.
Yes, Shikha.
Thank you, ma'am, for this wonderful session. Ma'am, I face lots of problem while preparing real
Shikha,
analysis.
could you please introduce yourself first?
Yeah, my name is Shikha, and I am from Birla Institute of Technology, Jharkhand.
Okay.
So I'm MSc student, final year MSc student.
Oh, okay, okay.
So while preparing real analysis, I face lots of problems. So I just want to know how to approach this subject so that I can prepare it well.
See, when it comes, for different papers, the way in which you can prepare yourself is different. Like when it comes to differential equation and all, most of the time, I'm saying in the perspective of net and gate. So when it comes to such exams, you have to learn the formulas that are given, the way in which you can solve a differential equation. It's just like direct application. But when it comes to other papers like analysis or algebra, that is not enough. You cannot always expect the question to be direct. So it can be indirect. So all the questions that I have chosen, I think none of the questions are using the results that I have discussed so far. So I have chosen those questions which are different from it, because those which you can directly apply. Of course, there are enough and more questions that use such direct results. So in order to do those questions, you don't need my help. You can just refer to the notes and then you can do it yourself. So in order to do the other type of questions, you will need more practice. So I'll suggest you a book. For theory part, Sherbat and Bartle's book, Real Analysis, that will be fine. And for doing more questions, Malik and Arora, Real Analysis. So in that book, you have enough and more questions, both as worked out examples and as unsolved problems. So the question that we have discussed in this, that is root of 7 plus Sn, that is there in that book. Then the last question that we have discussed, that is also there in that book. So that I saw many questions which were appearing for exams in that book, Malik and Arora. So that I'll be preparing that book very much for competitive exams. And yes, keep doing more questions. That's all.
Thank you, ma'am.
Yeah, Shikha, that is a point. You have to keep on doing problems. Also, you have to strengthen your concept base. Okay. You have to learn the concepts well. And also, whenever studying a theorem or a result, you should be very careful about the assumptions and the conclusions. whether all the assumptions are needed. If you relax one of the assumption, what will happen to the result? So that type of a thought process should be there while studying, especially real analysis. So an analytical mind is needed to solve the problems from real analysis. So should try to learn the concepts well and also try to practice maximum problems. Remember the words of the great mathematician P.R. Halmos. The only way to learn mathematics is to do mathematics. Okay, and there is a book published by American Mathematical Society, namely Problems on Real Analysis, something like that. That book is a good companion for any student who prepare for a higher level of competitive examinations in the area of mathematics. That is available in, I think, in the links shared in our groups. So please do check and inform me. Otherwise, I will share it. Okay.
Okay, sir.
Thank you, Shika.
Thank you, sir.
Yeah, others?
Thank you, ma'am.
Yeah.
Ma'am, could you once more say the name of the author and book?
Bartle and Sherbat, Introduction to Real Analysis, and Malik and Arora, Savita Arora and S.C. Malik. That book name was Introduction to Real Analysis itself, I guess. Real Analysis book. These are the two authors.
Yeah, Altaf, you can just keep on searching in Google with the author names.
Yeah, you just give S.C. Malik and Savita Arora, you will be getting the book.
Yes.
But one problem with that book is that they have flooded it with too many results. Don't get upset seeing that is when they are coming to limit supremum, limit infimum and all, they have taken too many results. Don't get upset with all those results. Go with only those which require that much attention. Almost rest of the results you can get it by simple calculations. Don't by heart it just because it is given the title as theorem. So go for only those results which are highly important. Rest of those you will be able to memorize it like corollary and all. You don't have to by heart fully. Okay.
Okay, ma'am. Thank you.
Okay, others?
Hello, ma'am. Sir, am I
Hi.
audible?
Yes,
yes, you are audible.
Yes, ma'am, I'm Anamika from Zamini's College, Kozhikode. And thank you, ma'am, for spending such a valuable time for us and teaching the different approaches in the questions in sequence. And it is really helpful for us to go through the different approaches. And we should thank Vinod sir for giving us a great opportunity to be with Nandana ma'am in such a wonderful class. Thank you, ma'am.
Yeah.
Thank you, Anamika. Others?
Hi, sir. Am I audible?
Yeah.
Yes.
Hi, ma'am. I'm
Hi.
Harita from Monotone College, Chungatra. First of all, thank you so much for this time. We are sure that you have a lot of works to do and still you are finding a valuable time for us. From the PPT, we know that you have prepared pretty much for this class. Thank you so much. Thank you so much for the effort. The theory part was a bit fast. I know that it's because of the time limit, but I will watch the video record.
Yeah, sure.
I think I will be able to catch it. And the problems was very interesting, and there was really different approaches. It's very valuable. Thank you so much. And we expect more classes from you. And thank you so much, Vinod sir, for such a wonderful experience for us and introducing Nandana ma'am to us. Thank you.
Thank you, Harita.
No worries, I'll be sharing the PPT to sir. He'll be sending it to you.
Okay, ma'am.
Thank you, Harita.
Ma'am, good evening.
Yeah, good evening.
First of all, thank you to ma'am and thank you to Vinod sir and all who organized this session. And ma'am, let us know your journey to success. Can you just explain?
Don't know if it's success or not. Still going on.
Okay.
I've done my graduation from Mercy College, Palakkad. I have got passed out during 2017. Then 2017 to 19, I did my PG from CUSAT. And after 2 years break, after 1 year's break, I got qualified for NET with JRF and GATE. That was in June 2020, NET, and GATE 2021, GATE. And in 2021, I joined in Amrita as research scholar, and I'm doing research in graph theory. So now I'm almost, my coursework is done. I'm entering my research area. That's all.
Wow, awesome. Thank you, Miss.
Yeah.
Thank you, Rania. This. Yeah, please do come forward if you want to say anything, to express any comment or.
I'm Malavika, third year BSc Maths student of Zamorans Gurarapan College. The class is very nice. Thank you very much, ma'am, for such a wonderful class and also for your effort. We really enjoyed your lecture. It was very helpful. Once again, thank you so much, ma'am. And also, I would like to thank Vinod sir for conducting such a wonderful class for us. Thank you, ma'am.
Thank you, Malavika. Any others? So we are almost running out of time.
Yeah, it's almost 9:05.
I appreciate Nandana for your perfect time management. You have finished the things by around 8:30, as I told to you. If there is no one again to express your views, we can wind up here. If any of you would like to ask anything with Nandana, you can do it now. See, don't feel shy or you can come forward and ask, no problem. Yes. So I think, yeah, many of them.
It's almost done, sir.
Yeah, many of them may be in short of their data also, as it is late night, almost late evening.
Yeah.
Okay, once again, thank you, Nandana, for being with us, for being with the family of Maths Aspirants Groups.
Yeah, sure, sir.
Okay, let us wind up here. So
Yeah,
I hope
okay,
that
sir.
you will do your next session in a nearby in 1 or 2
Sure,
weeks.
sir. I'll be arranging that.
Okay. Thank you, Nandana. Okay, let us
Okay.
wind up here.
Thank you, sir.